we want to look a little more at the derivatives geometric properties before we start looking at taking derivatives of a lot of functions. In particular, you know it's got to be related somehow to the function, and so we want to be able to relate the graphs of the function and their derivatives. So let's look at, here's a graph of a function, and I want to give a little demo here of what the derivative looks like. So remember, the derivative you can think of as being this surfing tangent line. So everywhere on this graph of f, I can attach a tangent line. And so you can think of it, if you want to think of it as a little video, that this is just surfing along that tangent line. And so you can see that the tangent lines are positive. You see that red dot that's kind of following? That's the actual value of the derivative. So if I were to evaluate f prime at, in this case, it looks like negative 0.4, that's the slope I would get. And then there's the graph of that tangent line, is the blue line, obviously. And so everywhere along here, you can see this tangent line. And so if I were to just trace that out, what that derivative is giving me, there's actually a corresponding graph to the derivative being given here, and that's in green. And so how does that green graph relate to that black graph of the actual function? Well, there's a few things we can see. We can see that when my tangent lines are negative, right, so the slope of that tangent line is negative all the way through here. Notice my function, my green function, is below the axis, meaning my derivative is negative, which makes sense because my derivative is giving me the slope of those tangent lines. And then right about there is where it switches from negative to positive. And so somewhere in between there, it's going to be 0. Well, you can see where it's 0. It's where that red dot crosses the axis. And then the slopes are positive on this side. And so when I go back and look at my graph, I can see that that's one nice way to see what's going on with my function. Where my graph has positive slope, has tangent lines with positive slope, my green graph is above the axis. Where my original function has tangent lines with slopes that are negative, my green graph is below the axis, and it crosses and is 0 where I see this sort of has a horizontal tangent line, which is that little bump at the very top, at the high point. You can see that it would have a horizontal tangent line there. So let's put that to work over here. So this says that I've got two graphs given. One of them is the function, one of them is its derivative. So from what I was just doing, I think what I want to do is if I have a place where it's one of the easiest things to pick out is where I have horizontal tangents. So it looks like there's on this one, for example, if that's my function f, that's a horizontal tangent line, which means if the derivative is this black graph, then that black graph should be 0 at that point because the slope is 0. The black graph should be 0. Well, that's enough right there to tell me that the black graph is not the graph of the derivative of the red graph. So let's try it the other way around then. Let's look at the black graph. Here, the black graph has a horizontal tangent. And if the red graph is its derivative, it better be crossing the axis, and we can see that it is. And it happens everywhere that the black graph has a horizontal tangent, the red graph is crossing the axis. So that's some evidence to say that the red graph is the derivative of the black graph. But also, remember the other thing is, look at the signs of those tangent lines. The slope is negative here, which means the red graph should be below the axis, and it is. And then it switches around in this area. My tangents are positive, and you can see that my red graph is positive, and so on. Everywhere I go, tangents are negative, slopes are positive. And so my red graph is, if I'm told that one of these is the derivative and one of them is the function, then this has to be the function, and this has to be its derivative, just based on where I have horizontal tangent lines on my black graph and where I have positive and negative slopes. So that's enough to distinguish in that particular example. Let's try another example. Okay, so one of these graphs is the function, and one of them is the graph of a derivative. So I don't have horizontal tangents this time, because the horizontal tangents in this previous one pretty much gave it away. If you're telling me one is the graph of the other, I can just look at the horizontal tangents and say, well, this one doesn't work because they're supposed to be 0 for if this is the function. But this one doesn't even have a horizontal tangent, so I got to do something else on this one. Well, on this one, I can look at slopes of the tangent lines and say that if this is the function, well, let's go down here. If this is the function, notice that's a tangent line, and that tangent line has a negative slope because it's leaning to the left. Well, this then cannot be the derivative because this function is giving me only positive values, which would say all the slopes are positive. So switch it around and try this then. So if I look at this line, this graph, and I say, well, there's a tangent line, that has negative slope. And all along here, the slopes are going to be negative, no matter how I draw them. And I can see they get steeper and steeper. Well, that's exactly what's happening. This is giving me negative values. And where these slopes start getting steeper, these negative values become more negative. So this is derivative down here because it's giving me that property, that it's giving me the right values. These are all below the axis, so it's giving me negative values, whereas it can't switch it around. I can't say, if I try this one, like I just said earlier, that's got a negative slope, but these have positive values. So this has to be the derivative down here. This has to be the function. Just looking at the signs on that derivative. The signs have to be negative to match up with the slopes that I'm seeing. So we'll try a third one. Okay, so this time, if I look at this graph, I can see that if this is the function, these slopes are negative. So this is giving me all negative values like it should if this is the function when I look at these tangent lines. But when I look at these, that tangent line is positive and this is giving me positive. So they're both matching up that way. So the slopes are right, whichever one you were to choose. It looks like this gives me negatives. This gives me the negative slopes of this graph if the blue graph is the derivative and that's the function, and vice versa. This is giving me positive slopes when this one's if f is the function and the red one's the derivative. So how do I distinguish which one's the function, which one's the derivative? Well, let's look at the behavior of the slopes on this one. These slopes are getting flatter and flatter and flatter as I go along here. So are these. Flatter and flatter, flatter, meaning they're becoming more and more horizontal. Well, if the slopes are becoming more and more horizontal, that means the slopes are headed towards zero. And so my derivative should be getting closer and closer to zero. And where that's happening is on this red graph. This graph is not getting closer to zero. It looks like it's getting closer to -1, which would say my slopes would be approaching -1 if this were the derivative. So this has to be the derivative because it's saying my slopes are getting close to zero, and you can see they are all positive, and this gives me all positive slopes, but they do get closer and closer to zero, the slopes do. So that would be how I'd have to distinguish those two. So keep in mind, slopes, when they're zero, when they get close to zero, when they're positive, when they're negative, and you can sort of distinguish between a function and its graph. So what we're going to do next is we're going to try to sketch a couple of graphs of derivatives.